within the JVM language and a deep internal flaw with that construct, and how it probably affects you even if you don't realize it, and some steps that you can take to avoid that particular problem from occurring. So to start off with, you may or may not be familiar with the finalized construct, but in case you aren't, the finalized construct is a method that you can implement on an object that JVM uses to call whenever a cleanup action needs to be taken. So essentially, you can have something that frees external resources or associated data memory or something of that nature, and when you want to be sure that when the object is gone, you can implement this finalize method. It's somewhat similar to the notion of a destructor in a non-garbage collected language like C++, although in that case it's a bit different in that you have a guaranteed call that happens from the language. Whenever a variable goes out of scope, it's immediately cleared. And so finalize isn't quite like that, and that's where we get into sort of the commonly known problems of finalize, that if you look around, you look at various articles or published materials, Effective Java, and so on, they'll recap these sort of general issues with finalize, and I'll repeat over here. I mean, one of the first ones is that finalize itself is slow, and it's slow because before the garbage collector can actually clear the object, it actually has to invoke a method, and for it to invoke a method, it needs to use a thread pool, and instead of just completely getting rid of the memory and moving on, it needs to wait for that action to occur. And so if you have an object where you're creating lots of them, say millions of objects or an object per request or something of that nature, then it can be a real performance problem with the garbage collector. They can be unreliable. The finalize, because it's called from a garbage collector, one of the things a garbage collector does is it defers memory collection to improve the performance of your running application. And so basically, if you have high load, it may put it off if there's plenty of memory available. And because of this deference can occur, the finalize method might never actually get called at all, or it might be very late. And then there's some dangerous aspects of using it. You have to remember to do certain things like chain the method callback to the parent. And if you don't, then a finalize might be called. So the way that most code should be written that uses any kind of resource that needs to be cleaned up is there should be some sort of a close method, and that close method should be called from a finally block. And then in Java 7, there was a new feature where you can do try with resources, where you essentially declare a block, and in the process of declaring a block, when that scope closes, then it will be cleared automatically by the actual JVM right over here. So you know, most legacy code will be using this try finally block, but in newer code you'll start to see try with resources, and that's a much better and easier to use thing. So if you're working with a resource, this will prevent most problems from occurring. However, there's still an accepted use case for using finalize in your application. And I say it's accepted use case because you can find a lot of resources that say, well, don't use finalize unless you're doing this particular scenario. And that scenario is what's called the safety close. And essentially, what it's saying is that in a garbage collection case, what you want is the user to use a try finally block. But they might not do that. And so in that case, instead of just letting the calling code leak a resource, you can put a finalize call on your object and then safely free it in that case where they forget to do it. And ideally, you want to do something like log an error message and say, hey, you forgot to close your connection or whatever. And then there's a variant of that where you can use native resources, and that's if you're messing with things like native memory outside of the VM, and you need to free those resources with the actual Java object that it's bound to. So with that brings me to this puzzle. And this is basically an example of the safety close approach. So we have a work method at the top that defines some action we're taking. In this case, we're writing to a file. And then we have a finalize, which safely closes it. And then we have the main method, which simply just executes the work method. So does anyone want to take a guess what happens with this puzzle? Well, it fails. And the reason it fails is because it won't always fail. There's a race condition. And what we can see in this exception at the top is that somehow in the middle of a write call, the finalize method somehow ran and closed the actual file before we actually finished writing to it. So this is a huge unintuitive behavior that's a major problem. And so to figure out why, it really helps to take a look at, well, what is the JVM actually doing? And from that standpoint, it helps to understand a particular implementation. So we'll look at OpenJDK. So there's some characteristics about OpenJDK that's interesting to know. Whenever you have a language that has a garbage collector that runs, and you have just-in-time compilation where you're producing native code, it's really easy for those two things to step on each other's feet. Because the native code that's produced by something as advanced as the JIT will produce, it comes from many different factors, like the actual runtime behavior of your application, what type of traffic it's doing, what type of actions it's taking, what type of CPU architecture you have, how often the method is called. All of these things influence what type of code the optimizer actually produces. And because of this, the garbage collector can't really know if the object, if the method that has been compiled down into native code, what things it's using. So there has to be some form of communication. So what OpenJDK does is it has this notion of what's called a safe point. And a safe point is where each active application thread can pause so that the garbage collector can do some final cleanup action. So that's the point in time at which the garbage collector knows all of these objects are now no longer around. Now they do some advanced algorithms around that where they can do things at the same time as your application threads are running, so they can mark and clear up most things, and then right at the end they can verify the assumptions are correct and then alter them and then finally clear. But eventually at some point you have some safe point pause. And these safe points can basically be any method call that your method makes. So anytime you make a method call, unless that call gets inlined, it's a candidate for being a safe point. And it can be other conditions, like if you have a loop, a big complicated loop, when there's a back jump from the loop, that could be a potential safe point. So in order to resolve the conflict between native code generation and the garbage collector, what the JIT does is it actually stores this thing called a GC map, which records at this point in time in the code, this is the actual set of objects that are still alive that I'm still using. And then from that, the garbage collector then knows what to do and which things can be cleared or not cleared. So if we look at our example that we had before, where we had a work method and then there was the stream that we're working with for the file, and then we write two different actions, we have safe points already because those things are potential candidates for being a safe point, so we can get the GC map afterwards. But just for the purpose of seeing what's going on, you can stick any old method call. So in this case, we've got a thread.yield in there. And then once we have that, we can then look at the details of exactly what is the JIT producing that allows you to understand exactly what are the lifespans that the JVM thinks are still valid. So there's a lot going on in this slide, so I'll just cover some general areas. So this section here with the black text, this is the actual assembly code. This is what's produced on a x86 64-bit processor by OpenJDK. And then it leaves these little comments here, this little semicolon, and this thing right here that says OOP map, that is actually our GC map. OOP is hotspot jargon for just an object pointer. And then below that there's a bytecode instruction. So the Java source code, or whatever JVM-based language you're using, it produces JVM bytecode. And then the JVM bytecode then gets translated into this assembly language here. And then to make it easier to see what's going on in this slide, I have a orangish brown text of the actual Java code that produced the above assembly block section. So in this case, our bogus method call that we just stuck in there just to debug is really just gives us this map here. And what we see is the very first assembly instruction, move RSI into RBP. what this is just following assembly x86 calling conventions, and it just means take the variable that I'm passed from who called me and stick it into the register RBP. And the way that Java method invocation works, that RSI contains this. So that's the reference to our object in our where we had our work method. And then if we look at the OOP map, it says right here RBP equals OOP. So that means I am using an object and it is stored inside the register RBP. So then when the garbage collector is running, it knows, okay, I'll just look in this RBP register and that will contain a live object, and I know that it's still reachable and don't clear it. Then in the next line of code, we just do a simple assignment statement, and that assignment statement gets mapped into just a memory move operation. So it just moves an offset for the stream field off of the actual object reference itself, because you can think of a Java object in memory as basically being like a big data structure, and there's like an index inside of that data structure, and at each index point you have a field. And so at this field is where we grab our stream, which is a file output stream, and it gets copied into RBP. So essentially RBP, if we just got crossed out, and now stream is inside of it. And then if we look down at the first method call here, this stream.write part 1, you'll see that the GC map just contains RBP once again. So basically what this slide means is that the second that this assignment statement was written, stream equals this.stream, this was completely removed from being reachable. So at this point in time, the entire object can be collected before any of this code down here runs, and this is the fundamental cause of why we get that particular exception. So to restate it, what this means is that if you have a finalize method on your object, it can be called while another method on your object is being invoked. And this is why it makes the feature essentially flawed. It means that even the safety close use case, which is regarded as the only last remaining use case for finalize, even that can fail, and probably is failing in code in many projects that have used the finalize feature. So this is affecting production systems now. And it also means that not only is finalize itself broken, but PhantomReference is also fundamentally broken, because PhantomReference is simply just another way to get a notification when an object is destroyed. But the fundamental behavior of the JVM itself is that an object can be destroyed before its methods have completed executing. So therefore, if you try to react to that object being destroyed and you do something with a resource that's still in use, then you'll cause the same potential issue of a closed descriptor, corruption, invalid memory data, and so on. So this problem affects the IBM JVM, and it affects OpenJDK. It's extremely common on the IBM JDK. On OpenJDK, it's not as common. It can happen once a method has been selected to be compiled into native code, which on the server compiler with C2 takes 10,000 invocations. So before 10,000 invocations happens, the code is not even compiled, it's just interpreted. And then after that happens, it has to pick a high level of optimization path, which may or may not happen. So that can vary based off of what the code is and other factors and how it's being used. And even then, in OpenJDK, the finalize thread that actually runs the finalize methods is somewhat delayed. So if it's like really, really fast, you may not actually see the problem, but it's still broken code and still will eventually fail. And I think it has failed in production for a lot of people, but they just assumed, they chalked it up to some sort of a JDK bug or something strange with the system, not realizing that actually the code is wrong, and that's what's causing this problem. So then the next question is, why is this behavior so unintuitive? And the reason is that the JLS spec itself that defined, originally the Java language was defined at the same time as the JVM, and in that definition it specifically says that any local variable that you're using on the stack can be cleared before you would think intuitively that it should be. So the assumption you would make is, I've written a method, I use 3 local variables, therefore when this method completes, that's the point in time when those variables go away. Well, just the way that Java is spec'd, those variables can go away sooner, which is fine when you're just dealing with the objects themselves. When it's just garbage collector clearing Java objects that are never referenced again, that's fine. It's not so great when you have the notion of a method call that happens in reaction to a close, where you can cause corruption. So basically, it's a good optimization. It just has some bad ramifications with the way in which Finalize was defined. Now, the good news is, though, is that there's actually some approaches you can take to dealing with the situation. You can work around the problem. The easiest first approach is to use Synchronize. There's a special rule in the JLS that says that if you use a Finalize method and you mark that Finalize method synchronized and all the other methods are synchronized, then essentially the finalizer will never run until all methods have completed. I mean, it words it actually in a much more precise way than that, but basically if there's a monitor that's can be acquired on the object, when the finalize acquires a monitor, then essentially it will not run the finalizer thread. And this was the intended way of dealing with this specific problem. So the problem itself was foreseen, and there was an approach thought up to deal with it, but that approach isn't necessarily the most applicable to applications today, and I'll get into that. And then the other option that you can use to deal with this is that you can actually make the optimizer think that your object is still alive, and that ultimately is the way that gets you the best performance, but it's a complicated thing to do, and I'll show you why in a second. So the synchronized solution, really simple. You have a finalize method where you've decided you have to use it. No big deal, just stick synchronized on every single method in your class. Some of you are probably thinking about, well, that kind of sucks, you know. And so there's the obvious negatives to sticking synchronized on everything, namely that you can't have concurrent code on that, because now every single work method call is now serialized with all other work method calls. And you also have all this overhead. Now you have locking overhead, you have barrier overhead, CPU fences getting called, and so on. Now on the plus side, though, the JVM has this thing it can do called biased locking, which is where if it figures out that the same thread is the one that's using the lock, then it can optimize away the actual lock contention queue overhead portion of it. So basically, if you were to use your object only in one thread at a time, then a lot of the contention overhead of synchronizing everything would go away, and you don't have to worry about it so much. But a big negative is you still have that memory barrier overhead. From every time you have something that's synchronized, it has to introduce latency into the call in order to deal with, you know, the coherency between multiple cores and multiple CPUs in the system. So you can deal with the concurrency problem of you want to support multiple methods, multiple work methods getting executed at the same exact time by using something like a read-write lock. So in this example, and this is actually kind of complicated, but basically what you do is you have the same notion of a synchronized block like before that's required, and at this point in time, this will prevent the finalize from running, and we can grab a read lock here. So if all work methods do this, then it will serialize it for just a little bit of time. It gets serialized just enough to acquire a read lock. And then once the read lock is acquired, then you can do your work method in parallel. And because of the rules that a monitor that's acquired on the object, any monitor that's acquired on the object, if the finalize has a monitor acquired as well, then it won't actually run. So then you know for sure there's not a weird condition where the finalize can run and get the write lock, and your work method can't run because it's waiting on the write lock to go away. So it's guaranteed order that the work method will acquire the read lock. You perform your work, and then at the end you release the lock. So the second part of this, though, is there's a problem in that if you have to acquire a read lock and a write lock to deal with the situation, to order these two events, then you have an issue where you can stall the finalize thread, which you don't want to do, because if you stall the finalize thread, you have to keep in mind that every single object that implements a finalize method has to be called from. On some VMs, it's a single thread. In other cases, it's a pool, but it's still just a few number of threads. So if you do something like you block in a finalize block for, like, say, I don't know, 10 seconds or something, then you prevent the GC for 10 seconds of being able to do any other finalize invocation. So that means that anything that has a finalize cannot be garbage collected for 10 seconds. So you never want to block the finalize thread. And in this case, since we're using a read-write lock, that would normally block the finalize thread. So then what we have to do is this complicated thing where we use an executor. So I created a static called Reaper here that's an executor. And then you kick off the cleanup task, which is what your finalize normally would do. And in that task, then you can hold your write lock. And so that will do the read-write ordering for dealing with this particular event. So I'm sure you guys are thinking, this approach is really terrible. And that's the big disadvantage. That's a very convoluted way to solve all of these problems. And so the question is there a better way? And to recap, now you have a read-write lock, which has more overhead than a normal lock. You don't have lock biasing on it, for one. You have the memory barrier overhead. You have the lock coordination. You have an extra executor and extra threads. It's not a pretty solution. So it'd be nice if we could just figure out a way to take the objects and make them last longer. And it sounds really easy, like, oh, okay, well, I'll make sure my object's still used. I'll just stick a field read right at the bottom of my methods. All my methods, I'll stick a field read. Problem solved. The object's still alive. Well, it's not that simple. The optimizer is pretty smart. It'll figure out things about how you're using your code, or maybe changing up your code without you realizing that that's an intuitive thing to do. So as an example, if I just stick a field read, like right here at the bottom, then it'll realize, you don't use this field, I'm just going to get rid of that instruction. It's a perfectly legal transformation for an optimizer to make. So now our attempt to keep it alive just failed. It may do other things. It may rewrite the ordering of instructions, which happens more often than you would like to think. I mean, this is the kind of the cause of a lot of race conditions in concurrent code in general. When you have to start worrying about like locks and volatiles and all those sorts of things, this is a huge factor. It's not just the different CPUs talking to each other. It's that the optimizer does certain tricks to make code faster. Almost all modern CPUs can do basically pipelining of instructions. So if you have multiple, say, initialization statements spread across your method, one of the optimizations that it will do is it can actually take all of your initializations and stick them all at the top of the method, because the CPU can pipeline all those instructions together and initialize multiple memory areas at the same time. Like it's a 32-bit value, you've got a 64-bit element in your plane, you can just write two 32-bit values at that point. So in this case, what we had is we're trying to be more clever now, and we stick this write here in our work method, and then it says, oh, you know what? I realize that these two write methods do never actually use this trick field, and there's no other activity in the application that would ever use this trick field. So therefore, I'm just going to move it above the write call, and then we once again our attempt to trick the optimizer into keeping the object alive fails. So a solution is similar to how you could solve a concurrency problem. Because concurrency problems have the same sort of issues where you don't want instruction reordering to happen, you can piggyback off of a volatile field. So since Java 5, they wrote a full memory model in the Java specification, JVM specification, that describes various principles. And one of the principles they define is what's called happens before. And there's certain constructs that say that when you do this construct, anything you did before it happens before. So in other words, there's a guaranteed program order rule. So the program order rule says that when I do a write to this volatile field here, there's a guarantee that all these instructions above must come before it. So the optimizer cannot reorder those instructions. Now, since can be a little paranoid, and a future optimizer might still say, well, you're incrementing this field, but there's still nothing else, even though it's volatile and all that stuff, there's still nothing else that actually uses it, and maybe it can prove that the memory effects that come from writing to a volatile field actually do not benefit the program in any other way. So to work around that, what you can do is you can just create a public static field that's initialized, or sorry, not initialized, that is set every time, written to every time by the field that we're maintaining here. So we have this counter field which simply acts as a trick, and then in the finalize method we can initialize a static counter to be this counter field. And since it happens in the finalize block, you could do it to where it only happens when the user forgets to close the resource. So this safe close method that I have here, all it really is doing is it's saying if stream is closed, then don't actually close it. And you can then use the return value to say, well, if the stream was closed, so the user forgot to close it, then we take this overhead of writing to the static field. And because it's writing to a public static field, and because Java says that you can load code dynamically, you can do a class loader and load some new classes, and the new classes can do new stuff. That new stuff might read this static field, and if the optimizer ever eliminated this if it ever eliminated this field, which is used to generate the value of the static, then it would never, then it would have an incorrect value. So basically, in order to optimize this particular construct away, you would have to eliminate the notion of runtime statistics gathering, which is, in every single enterprise application in the world. So they're not gonna do an optimization path for that. And the benefits of doing it this way is that you have no locking overhead, and you don't have to worry about concurrent. So you don't have to worry about concurrent access. But it's kind of delicate. I mean, you can kind of see a situation where you write some code like this, and then maybe it's an open source project, and you have a contributor who comes in, and they're not going to know why you did this. It's not going to make any sense. So you'd want to comment the heck out of it, say, do not delete this. Do not delete this field, and then you could see, but that could happen with the synchronized solution as well, right? Like someone might create a method and they're like, well, there's no need for this thing to hold a lock, so why would I mark it as synchronized? So you just remove the synchronized attribute from that field. So this is a general, in any solution you take, this is a problem, but it's worse, I think, in the volatile solution because of the fact that it's so strange looking. And then we still have this barrier. When you write to a volatile field, it does this special CPU fence called a store load, and what it means is that when one core on a CPU writes to a memory area that's what happens is that if it's a volatile field, it gets mapped into some special calls that allow it to wait until other cores in the CPU or other CPUs catch up and are working on the latest information. So the whole idea is that, like, if I've got two threads, they're both caching values, and one of them writes a number into one thread, then the other thread won't necessarily see the correct value. So a volatile write requires that they essentially agree with each other, and requiring that introduces latency. So it has write latency, which is not great. What we can do is we can actually cut out the write latency. We can use a notion called a lazy write, and what that does is it changes the memory barrier from a store load, which has that annoying latency effect, and it can do what's called a store, which just means that when a write to a variable is made, another write will have to be after it. So it's basically the CPU as a whole has to agree on the overall ordering of write operations. And on x86 and other CPUs like Spark, it turns out that they're already ordered that way. So basically a store, which is what the lazy write is completely free. All it does is it just restricts the actual write action to not be reordered relative to all other instructions. So in other words, it does exactly what we want it to do. It gives us a way to trick the optimizer into thinking that the value of the object is still, or the reference to the object itself is still around and still in use. So big advantage, it's got great speed or great performance semantics to it. It has no locking overhead. It has essentially a free barrier on most architectures. Some architectures like ARM, it's a little bit different, but it's still relatively cheap. And but it is again this very alien-looking sort of thing, and it's one of those things that you would want to comment. So you may be wondering, well, this is really crazy, and why can't we just fix the language? Why can't we just fix Java, fix the spec? And the problem is that optimization that makes it so the garbage collector can clear memory fast if it chooses to do so. If you were to take that away, it could have all kinds of negative effects on applications that are running great today. that are scaling well today. So I think it's very unlikely that anyone would ever consider adjusting the lifecycle aspects of objects. And even if it did happen, it would take a long time to get the behavior in. It'd probably be like 2 or 3 JDK versions, and we still have to deal with this problem today. So there's not much we can do in this area other than adapt to it. There might be a little shred of hope in that if the JVM was to introduce a little method call called keepAlive, if you could just say system.keepAlive and say this or any other object that you want to keep around, and that could be translated into a hint for the JIT code to not eliminate the use of that reference, and that would solve all our problems, and it'd be nice, clean, easy to read code. So this would be the ideal solution, I think, to this problem, other than not using Finalize at all. But if it is going to be used, it'd be nice if this method was added. So it's something I'll advocate, and I think it would be a great benefit. So in conclusion, I hopefully accomplished the goal of making you guys being very wary of ever using Finalize in your code, ever for anything. And then also, I highly recommend that you audit your code. Any project that you're using, you may want to look at this. If you see weird stuff happening on a system with things getting corrupted or closed or whatever, that could be a sign of this particular problem. And this is a problem that actually affected the Wildflower project, which is why I got so interested in this, is because we found this. And in our case, we can't just get rid of the use of Finalize because there's a lot of API contracts that require that you do it. Like JNDI, for example, the naming API in Java. You can look up names, and you can use connections to make a JNDI connection to another server, or it could be an LDAP connection where you're looking up resources. And that actual lookup call has to use a connection, and when you're done using your context, your JNDI context, that connection has to be cleaned up in some way. There's a method they created on the context interface itself called close, but hardly any code, if you look around, you'll see hardly any code ever calls the close method at all. And then right there in the Java doc it says something like, this is the close method, you should call it so that it can clean up resources, memory resources or connections or whatever. But if you don't call it, then the garbage collector will clear it. So basically it mandates that any provider that implements JNDI has to implement a Finalize method. And there's other examples of this too. Like I think the JDBC spec has something. I was just talking to someone the other day. It has some element that it requires it. So you may not have a choice in the matter. And then if you've done it before, it kind of becomes the contract because people sort of expect you to clean up their stuff for them. And and that's a problem. So there are cases where you legitimately need to use it. And then if you do it, I would recommend the synchronized approach if you don't need the performance, just because it's the easiest. It's not as convoluted. Otherwise, if you do need the performance, then the volatile plus lazy write solution is a good way to solve the problem. And this applies to phantom references as well. So any code where you see a phantom reference, this is the same thing you have to worry about. It's an overall behavioral issue of the object. And then the next thing is you can save yourself from this problem even if you have a broken Finalize method in a class somewhere if you simply use the try and close combination either through try with resources or with the finally block. If you do this, it will keep the object alive, and that will keep the problem from happening. So in a nutshell, when you're using any API that involves resources, always use a try block to clear it safely, explicitly. JNDI, for example, you should always call context.close. If you do that, this problem can't happen. It's only in the case where you have code that doesn't do that by mistake, or maybe intentionally it wasn't done because it just wasn't known, or you're designing an API and you are trying to cover the cases where other people forget. Then you have to worry about how should the Finalize be implemented correctly. So I have some examples on GitHub. On my user account. It's probably hard to read, but I'm going to make sure it gets this. When the slides get up on DevNation, you'll be able to click to it. But it's in1. There's a 1 instead of the I for in1 HILITY for the username, and then it's Finalize examples. And I have essentially an example that shows how it's broken, how it can be broken. You can run this you have to have the right JVM parameters on OpenJDK to get it to compile the code. You can also run an IBM JVM and it'll happen immediately. And then I have examples of all of these approaches and how you can use these approaches. And then it uses print statements so you can see the sequence of events like, okay, it's messing up here. And on Twitter, I'm JT Greene. I say interesting things sometimes. And then wildfly.org is where I have my blog and other information. And important news is on the actual Wildfly project. So mandatory plug there. And with that, if there's any questions, I'd be happy to answer them. Yes?
So this is only a problem when the JIT compiler kicks in and generates a native code, or the finalize call.
Yeah, so the question is this only a problem when the actual JIT compilation takes place? And the answer is not necessarily. The IBM, on OpenJDK, the answer is yes. On OpenJDK, it only matters if JIT ran and it was aggressively compiled. On IBM, it can happen in interpreted mode. And that's because they aggressively optimize lifespan even in interpreted mode. So it can actually affect you even if it's not a heavily used method. Any other questions? Yes? Uh-huh. Yes. Yes, so basically what, let me put that example right back up here. Basically what happens is that, I could tell you that if you didn't do that step, it would actually work based off of the combinations I tested, but it's still possible that the optimizer might remove, it's like one down here, might actually remove the field altogether. So it's really more of a paranoia thing, as sort of a precautionary measure to prevent it from happening. The static field contains garbage. So I'm not sure if you're wondering about a security concern or not, but the disadvantage to the static field is that the write to it will have a cost because everybody's going to be writing to the same memory area. But if you only write to it in the finalized block itself, then you're only going to be doing that cost of that memory write when someone has forgotten to close something properly. So it's a kind of a trade-off, I guess. It's not. I don't think it's a huge thing because you can have multiple threads writing at the same time to the same area in memory, and you don't have any sort of concurrency constructs or fences or anything like that. But so the only purpose of that field, though, just to restate, is just to keep the compiler from thinking that the counter field can be removed. But as I mentioned, I did not, when I ran these scenarios, the current implementations I've used to date have not implemented a strategy like this, but it is potentially possible to be done. So better to err on caution. Okay, so so private versus public. Okay, so the reason why it's important that it be public is that the optimizer can treat private fields as being irrelevant if it can, because it knows all of the access within the object because that's the private scope, and so it can easily say, I can eliminate this because nobody else uses it. If you make it public, then it has to worry about outside users, and it could even optimize those, but not fully because at any point in time, dynamic code can be loaded, and dynamic code that's loaded can refer to a public field, and so therefore it has to keep the value alive. So that's why public is important. It might work with protected too, but I don't think it's a big deal. Any other questions? Okay, well, thank you guys for your time. I'm hoping that through this presentation that you gained some valuable insight into this problem and to the way the JDK works, and that you can share that knowledge with your colleagues. I think it would be a great thing if all code that's out there, especially anything that's open source, if we can get all usages either eliminated or correct, then that would help anybody using the projects and all the consuming projects that build on it. So it'd be a great thing. Thanks.